Okay, all right. Let's get started. This survey, I'll go ahead and tell you, I asked a question again about the manual. I think that it's probably not an issue. I did some quick polling before class, and it looks like just about everybody that had not yet acquired a manual has gotten one, or it's like on the way. One thing I will tell you is I've assigned homework 1.2. It'll be assigned at noon. It's due Wednesday. We're not gonna have to do Monday, but I'll show you what the assignment is here in a bit. But it is basically just a getting familiar with the manual assignment. I mean, I'm literally asking you to look some values up in the manual so that it forces you to open it up and get a little bit familiar with it. It's a very basic assignment, just like the last one. I think everybody found the last assignment probably pretty easy. This is just sort of, getting our feet wet and getting familiar with steel design. I went ahead and posted the attendance grades. Everybody was here for both lectures, so that was pretty easy. So with that, let's go ahead and get right into it. What we're going to do today is talk about really two things. The first is the manual. Okay, I kind of want to talk about this thing because I see most everybody brought it, and when you look at this thing, it's intimidating, right? It's huge. The amount of data and design aids and specifications, the thing is just kind of ridiculous. And I want to break it down a little bit and have everybody sort of get a little bit more comfortable with the manual, because I don't want you to be overly concerned with it, because it really is there to help you. It's not there to get in the way, okay? So I want to first off very briefly introduce AISC. So AISC stands for the American Institute of Steel Construction. I don't think there's any way in the world you can forget that, because it is literally on the cover of the book. But AISC is somewhat akin to ASCE. So if you remember ASCE, I said that part of their purpose is to serve as sort of a means of warehousing and logging technical specifications for civil engineering. ASCE handles general civil engineering needs. These folks handle steel design. That's what they do, okay? Now the American Institute of Steel Construction, I would say that traditionally they have been primarily focused on building design, although here very recently they're really starting to expand their interests and horizons into the bridge market as well. They have a sort of a subsidiary organization called the National Steel Bridge Alliance that really serves a lot of the same purposes as AISC does, just for bridges. Yes, sir?
Does the IBC refer to this book, or does it contain some of this?
The other way around. It's the other way around. This refers to the IBC. So the ASCE 7 and the International Building Code have a lot of the same provisions in regards to LRFD load combinations and things like wind loads and snow loads and things like that. A lot of that's the same. So what this will do is reference the IBC. So it'll say, in the very beginning, here are some other specifications that this document conforms to. So for example, the International Building Code, ASTM. How many people here have had CE 321? If you have, you know what I mean by ASTM. So this document is sort of in accordance with a lot of those other provisions. That's a really good question. So the short answer is yes, they're all birds of a similar feather, as it were. Or feathers of a similar bird.
Thank you.
I haven't had much coffee today, which is a problem. I'm an engineer. Coffee's one of the 5 food groups. All right. So, okay. So AISC, just like ASCE, publishes a lot of technical manuals, design guide specifications. One thing I would actually really strongly encourage everybody to do is, you all had to create a student account for AISC in order to get the manual, I believe. I would use that thing sometime between now and the end of this semester to acquire the design guides, okay? So what I mean by that, we are going to cover the fundamentals of steel design, okay? But every now and then, as a steel designer, you're going to run into things that are like common, but not fundamental. So like as an example, I'm going to teach you how to design steel columns, but what about designing steel columns that are encased in concrete? or concrete filled tubes, as an example. Well, there's a design guide on that, okay? Now, if you want to buy that thing, I think it's like $50. If you're a student, they're free. And you can download like all the design guides as a student for free. And it's like a lot of money, like that you're not having to pay 1 cent for. So I really strongly recommend that you download them just to have them. They're really good. They're really good references. I'm actually going to mention some of them later in the semester. Okay, let's talk about the anatomy of the manual, okay, because this thing is huge, okay? So the first thing I will point to, if you have your manual, get it. If not, just sort of pay attention. So my manual might be a little bit distracting, given that I've got all these tab inserts referencing given sections of the spec. But the first thing that you should probably notice are these little black and silver tab inserts, right? Does everybody see that? So, for example, you'll see one that says DIM, and then one says GEN, and then one says beam, one says column, one says TEN. Does everybody see that? Okay, so the manual is split up into 17 parts because everybody brought their AISC 15th edition steel construction manual class, right? I know some of you are waiting for it to ship, but some of you I know have them and didn't bring them, and I'm gonna. I won't do that anymore. Just kidding, I will. So the manual is split up into 17 parts, but I think it's a little easier to sort of discretize what they represent, okay? So the first two parts, the part that says DIM and the part that says GEN, is the part that is the section of the manual that contains all of the dimensions necessary for steel design, as well as all of the material properties. So we're going to spend a lot of time in part one of the manual. In fact, I can tell you just about every single homework assignment this entire semester, you're going to be looking at part one, and a particular reference in part two. You're going to be looking at it all the time, okay? Parts 3 through 15, everything in the middle, that's really what you paid for, okay? Those are the design aids, and those are the design aids related to beam design, column design, bolted connections, etc. Okay, so I'm going to show you one of those here in a bit to kind of make a point, but that's really what you spent your money on, were those design aids. Part 16 is a section in and of itself. Part 16 is the specification. If you look at the tab insert, it says SPEC for spec. That is the specification and the commentary, okay? That is the document that is sort of the law, as it were. That is the section that contains the provisions and specifications that detail how exactly you are to size beams, columns, connections, etc. to safely resist loads. So everything that we do this semester throughout the entire course is going to be in accordance with what Part 16 says, okay? The name of that specification is AISC 360. So if you ever hear me use the term AISC 360, that is the name of the specification for structural steel buildings. In fact, the description of this course says design of steel structures in accordance with AISC 360. If you took concrete design, did you ever hear Dr. Zatar reference ACI 318? Did you ever mention ACI 318? That's the code for concrete, right? That's that document, for those of you that take concrete design, ACI 318 is the document that tells you, well, your stress block is A wide and A equals beta 1 times C, and here's how you calculate phi, and here's what development length is. For those of you that had concrete design, you know what I'm talking about, right? Yeah, so if not, if you take that later, you'll get what I'm talking about. All right, so I want to flip through some of the sections in the manual, and I kind of want to get acquainted with what these things look like. And so the first thing I want to do is I want to have everybody open table 1-1, okay? So table 1-1 is the section of the manual. So first off, table 1 is the section of the manual that contains all of the dimensions and details associated with all of the hot rolled products that we as steel designers use in steel construction. Okay, and so I'm going to talk here in a bit about what exactly those parts mean, what they represent, or what the different types of hot rolled products that we use in the United States. But this is a perfect example of one of these types of references in the manual. Okay, The first thing that I really want everybody to point to and pay attention to is this, okay? This schematic here in the top left, okay? So this schematic will tell you graphically what the data in this table represents, okay? So like as an example, so if I have an I-shaped section, okay? And I have an I-shaped section, and let's say that I want to know what this dimension is right here. There is a name for that dimension, okay? In the terminology of steel design, we call that B sub F, okay? And that stands for the width of the flange. We don't use W, we use B. It's like breadth of the flange, okay? One of the things that I will say that steel design, and this is kind of true about structural engineering. I think structural engineering can really sort of wear this with a badge of honor. Structural engineering does a really good job of maintaining consistent notation across the board, okay? So if I ever use the symbol B sub F, it always means flange width in just about any specification related to structural steel design. Whether it's the building spec, whether it's the AASHTO LRFD bridge design specification. You know, like in AASHTO, you might see something like BFC or BFT. All that means is the width of the compression flange or the width of the tension flange, but it all means the same thing. So steel design does a really good job of maintaining consistent notation. Okay, so I think that's something that's worth mentioning. Okay, so you can always, if you're confused as to what a dimension means, always refer to the schematic. I think for most I-shaped sections, it's pretty easy, but sometimes for some of the non-symmetric shapes, you just want to make sure that you're understanding what it's referring to with given axes, etc. Now, one of the things that you will find for a lot of the shapes in the manual is this, okay? So I'm looking at a W27 by 129, okay? Some of the more astute observers will see there's a little C note on that shape. You don't know what that means yet. You will by the end of the semester. Essentially what this means is that this has local buckling issues for this shape, but we'll get to that later. But if you look at the W27 by 129, one of the questions you might ask is, what is the depth? How tall is it? So here's the I shape. How tall is it? What is this dimension here from top to bottom? Okay. And one of the things that's kind of strange is there's two answers. Okay. So it says it's either 27.6 or 27 5/8. You're like, which is it? Okay. So the answer for us is 27.6. Okay. There will always be two reported dimension values, and the reason that they're reported that way is because of their context. Okay. 27.6 in this case is the value that you use for design computations, okay? The fractional values is what you're going to use for detailing. In other words, drawing, drafting, things like that. The idea is that if you're out in the field and you have a W27 by 129 and you pull a tape measure, ask somebody how deep it is, they're going to say 27 5/8 because if you've ever used a tape measure, you're going to call it on the closest tick mark on the tape measure, okay? But for the purposes of design, that's what we can hang our hat on to do calculations, okay? So if you're doing a homework problem and I see 27 5/8, I'm going to go, nope, that's wrong, okay? So for the purposes of calculations, you need to be using the design values, not the detailing dimensions. Does that make sense? Yes, sir.
Does that also, maybe I'm overthinking this a little bit too, but 5/8 would be 0.625, so if you use the 27.6 value, doesn't that, although minuscule, doesn't that alter the value to where you can over-engineer it per se?
Hence why I want you to use the design dimensions and not the detailing dimensions. That's exactly right, honestly. I mean, that's really why. But that is one reason. I mean, the short answer is, if you start rounding up some of those minuscule dimensions, it could cause you to pick the wrong shape, right? But in the end, the long and short of this, those are the values that we use for designs. That's what you need to be using, so. Does that make sense? All right. Any questions about this? Okay. Now, if you just start flipping through the main body of the manual, and you can pick any of the design aids, it doesn't really matter. I'm looking at a design aid in section 7. I don't care what design aid you look at. They're all going to kind of look something like this. okay? And you're gonna see references to green numbers and blue numbers, okay? If you happen to have color blindness, we're talking about the numbers that are shaded versus the ones that aren't, okay? The ones that are shaded, or the ones colored in green, are the ones that are referencing allowable stress design, whereas the blue numbers, or the unshaded numbers, are the ones that reference LRFD. In this course, we are going to use LRFD, okay? So just point blank, full stop right now, we're not using the green numbers. We're not using the shaded numbers. We're using the blue numbers in this class from here on out, okay? There are some steel design professors that like to have people, or students, use both design philosophy. Personally, I don't really see much value there. I think you just kind of need to pick one and go with it. And I think what you're going to find, honestly, I think that LRFD or AISD is going to start to be phased out with time. That's sort of my prediction. So, excuse me. I mean, I think we need AISD as a reference for rating structures, but for the design of new structures, I think everybody's going to be using LRFD, which is why we're going to be using the blue from here on out. Okay, so far so good? Okay, now I think I mentioned a little bit of this in a previous lecture, but part 16 of the document is again sort of the third section of the document that I think is really important to mention now, and that is the specification. Okay, now the specification, first off, if you go to Blackboard, I have a PDF of this specification that you all can download today. That AISC makes that available for free. Okay. What you will find is that the section is split up into two main chunks. There is a code and there is a commentary, okay? Now, what you'll find is that sometimes specifications will organize those into separate sections, like the steel manual does. Some specifications will actually list this side by side. I'm not sure if Dr. Zatara, if he printed out sections of the code in class, but if you look at the ACI code, the building code for concrete, you'll find code and commentary right next to each other on the same page. Basically, the way this works is the main body of the spec is the code, and then this section with the gray is the commentary. So like, for example, if we're looking at the chapter E in the specification, so chapter E is the chapter on the design of members for compression. So the design of members for compression are things like columns. And so section E1, this is what we use as designers, okay? And so what it's telling us in section E1, as an example, is that our resistance factor for columns in LRFD is 0.9. So the code tells us what to do. The commentary tells us why we're doing it, okay? So as an engineer, if you're looking at this and you go, why is the phi value 0.9? Go to the commentary. It will explain why. It goes into the background, the research. So for example, you can see here the history, how the resistance factor was increased from 0.85 to 0.9 in the 2005 specification. So before 2005, this value was 0.85, now it's 0.9. So imagine you're a steel designer and one day, you get a new manual and the value changes and you're like, what the heck happened? Go to the commentary. It'll explain why that happened. It'll point to all the studies that were done, the research that was done. Sometimes codes change as a function of real life events. Maybe some structure failed and it forced the industry to take a look at it and see maybe we should improve our models, improve our specifications. So again, the code and the commentary are really important marriages in structural engineering specifications, if you were. So we're going to be looking at the code quite a bit in this class. We're going to be referencing it, and a lot of the models that we use for tension members, compression members, come from the code, okay? So if I just throw some random equation out there and I just say, oh, FCR is 0.658 raised to the Fy over Fe all times Fy, and you're like, where did he come up with that? It's in chapter E, it's right there, so I didn't just make it up. So, does that make sense? Everybody with me so far? Okay, any questions about the manual? All right, before I get into some properties of steel, I want to show you something real quick. All So this is your homework assignment. It is again going to be like, it is going to be just like the last homework assignment where there is a quiz on Blackboard that you type in the answers. But basically what I'm asking you to do is go to a W30 by 261, what is the flange width, right? Go to an L5 by 5 by 3/8 and say, what is the radius of gyration about the z-axis, okay? It's just forcing you to open the manual and get a little bit familiar with it, okay? So this will turn live on noon. There are 10 questions. Some of them are typed in values. Some of them are multiple choice a little later. But again, I think that if you've got your manual, this will take you about 5 or 10 minutes to do. It's really not that difficult. Sound good? All right, so this is going to be your homework assignment. Okay, all right. I want to spend the remainder of class talking about like actual steel itself, okay? Now, for those of you that have not taken CE 321, I want to talk about how steel is made. And if you're an engineer and you've never seen an episode of how it's made, like I think you need a hug. I mean, it's like the best show ever.
You're not mad, you're just, are they still making it?
I think so. I don't know, but there's, I think, 3,000 episodes of it, so, you know, you could get lost in it. You know, it's like, you know, it's 2 o'clock in the morning, you're like, oh, that's how cotton candy was made, you know? I'm just kidding. I've never done that. I don't know what you're talking about. Okay, so I do want to mention a little bit about structural steel, and then I'm going to pull up the video. But one of the things about structural steel is that it used to be manufactured largely through the production of raw steel, like actually getting iron out of the earth and producing structural steel from raw materials. We're not really doing that so much anymore these days. We produce a fair amount of steel in the United States, and so a lot of the more modern structural steel production facilities in the United States, I mean, yeah, they're steel mills, but they're not so much producing new steel from raw materials as they are melting old steel and producing new steel from scrap. So essentially recycling old steel. So this video covers that process. What you'll see is a lot of scrap melted in what's called an electric arc furnace. Okay, so we take a lot of scrap steel, we melt it in an electric arc furnace, and then once we assess the chemistry, the metallurgy of that steel to ensure that it conforms with the specifications of whatever, you know, ASTM standard we're trying to match or whatever ASHTO standard we're trying to match, we then cast that into new steel components. So I have a really cool video. I'm going to show that. So let me pause my recording and then we will get to that. Give me 1 second. I guess we're going to have to just have y'all look at that later. That's sad. Man, I'm disappointed. So the video's right there. I included the link in the lecture notes. The lecture notes are available on Blackboard. I would check it out. I mean, if anything, I just hope it doesn't cause you to binge watch how it's made for, you know, a period of like 8 hours and you forget to do a homework assignment. My apologies. But long story short is that essentially what we're doing is we're melting old steel to produce new steel these days. Now, for those of you that have had CE 321, I'm assuming this isn't news to you. This is the stress strain curve for structural steel, right? And everybody, I'm assuming, has seen a stress strain curve before, I would hope. I know I showed you one in Engineering 216, right? But to back it up a little bit, so just to make sure that everybody is on the same page, because I know Engineering 216 was everybody's favorite class. What we have here is the stress strain curve, and this is a schematic showing the stress strain curve for structural steel. What you find, so what happens here? So what we do is we take a piece of steel, we take it down to the lab, and we yank it apart. And we yank it apart in a controlled rate, in a controlled manner, and then we record how much load we're putting on the system, or how much load we're putting on the bar, and how much it deforms as a response. So we record the load and deformation as the load is increasing. And then what we do is we take the load, we divide it by the cross-sectional area, we take the deformation, divide it by the original length, and we produce this stress strain curve. Because all stress is load per unit area, and all strain is deformation per unit length. Okay, Now, what we find when we load structural steel, as we increase the load, the very initial behavior of structural steel is what is called the elastic range, okay? In this range, steel really does behave like a rubber band. You take a piece of steel, you load it, if you unload it, it snaps back to its original state, okay? More often than not, in the land of structural engineering, we try and limit loads and resistances. We try and keep things in the elastic range if we can. A lot of our service limit states will maintain elastic behavior. However, our ultimate capacity calculations, our strength calculations, tend to reference worst case scenarios like fracture and things like that. Now, once we get past the elastic range, we then start getting into the inelastic range. Now, can anybody tell me what is the difference between elastic and inelastic behavior? So if I take a piece of steel and I load it past the elastic range, what happens if I unload it? I have permanent deformation locked into the member, okay? And that's what happens when you get past yielding, okay? Now, what happens for steel is right as you pass the elastic range, we have this plateau region called the yield stress. This is when the element has, we've passed the elastic range and we enter this plateau region. It's called the elastic perfectly plastic region, where as we've loaded it, those molecular bonds start to fail, and the element starts to freely deform under a constant load. But as the element is deforming under that constant load, those molecular structures are realigning, and once we hit a certain point, the element can start accepting load again. And so that's what we call the strain hardening range. Now, we find that there's a point when the steel just sort of gives up. And once we get past the ultimate tensile stress, we see that failure is starting to happen. We start to see significant change in the geometry of the steel element. We enter what's called the necking range. As you're yanking it, the middle sort of shrinks in, and then the element fractures. For you football fans, one of the things that you find about steel is that it exhibits a significant amount of ductility. Ductility is a measure of an element's ability to withstand permanent deformation. So if you were to imagine this is a football field, right? This is one end zone, this is another. From here to here, that's about the 1 yard line. And then from here to here, that's about the 10-yard line. Steel has a remarkable amount of inelastic capacity, which is really, really important in certain design considerations. So for example, when we are designing in earthquake-prone regions, we have to design structures such that they have a significant amount of ductility, because when an earthquake rocks a building, that sucker wants to fall down. So if we can withstand a lot of that energy and absorb a lot of that energy through inelastic deformations, that's great. So steel's really good about that. Now, a couple things. I already told you that the unit weight of steel was 490 pounds per cubic foot. I want that number burned into the back of your head by the time you graduate from Marshall. Another number that I want burned into the back of your head is the Young's modulus, or the elastic modulus of steel. Does anybody remember what the elastic modulus is? What is the elastic modulus?
It's the slope of the line in the elastic range.
Exactly. It's the slope of this line in the elastic range. It is the proportional constant that will tell you how much strain you get as a function of stress in the elastic range. And for steel, that is, or for structural steel, that is 29,000 KSI, or 29 million PSI. That doesn't mean steel can withstand 29 million PSI. It just means that the rate of change of deformation as a function of stress is at that proportional constant. Now, what you will find for structural steel is that steel comes in different grades, right? There's A36, A572 grade 50, A992. There's all sorts of different steel products, structural steel products. I don't care what structural steel grade you're looking at, they all have tend to have the same Young's modulus and the same unit weight. What changes from grade to grade is your yield stress and your ultimate tensile stress. So we call those terms F sub Y and F sub U, okay? When you look at different grades of steel, that's what changes from grade to grade. So I want everybody to turn to table 2-4 on page 2-48. If you want your first tab in the manual, this is it. And this is a good little exercise right now to make sure that everybody can find this. Okay, this is good. Looks like everybody's finding it. Okay. Now, there are two reference tables. This is table 2-4. If you flip the page, or on page 2-48, if you flip the page to table 2-50, so this is the one that is the material specifications for various shapes. And then the next page will give you the material spec for plates and other elements, things like that. Okay, so this is a good little reference to start flexing our steel design muscles. Okay, so if I were to ask you, what is the yield stress for A36 steel? What is it? I have it highlighted here on the slide, but you know, it's 36 KSI. Does everybody see that, right? Yep. Now, what if I asked you what is the ultimate tensile stress? Well, there's a range, right? From 58 to 80. If I was designing a structure, which value should I use? Okay, ooh. Controversy. We have some people saying 80 and some people saying 58. How many people say 80? How many people say 58? 58 is the right answer. Okay, and let me explain why. All right. First off, so what is this value going to be used for? I'm going to use this value as a threshold for determining how much force an element can withstand before it fails. So if I want to ensure the design is safe, I want a worst case assumption. In other words, what happens if I design a tension member to withstand load and I assume 80 KSI and it's actually 58 KSI? What happens? It fails, right? And I don't want any, if I'm designing a bridge that my grandma's going to drive over every day, I don't want anything to happen to grandma, right? So what I'm going to do is assume the worst case scenario. Okay, so the worst case scenario is 58. Now I can already see that look on some of your eyes going, why put the range, right? If you always want us to use the smaller value, then why put the range to begin with? Why are you making it so complicated? Just make it simple. Give us the value that we need to use for design, okay? That's a very fair question, okay? And I'll tell you why the range is there. The range is there to inform you indirectly of a material's ductility, okay? So what you will find when you produce steel is that, you know, as you're producing it, you do quality testing on heats of steel as the steel is being produced. You do a stress strain test on given steel coupons, and you're going to find differences in variability in tensile strength. Okay, what you find in steel is that as the tensile strength goes up, the ductility goes down. Okay. How many of you have ever heard of the Northridge earthquake? How many of you have heard of that? In California, yeah. This was a major earthquake in 1994. Okay. Now the steel industry was telling people during the 70s, 80s, they were saying use steel moment frames all the time. Okay. They were saying use them all the time because steel moment frames are incredibly ductile, and ductility is a parameter that we really like to see in earthquake design. That's great, okay? Now, here's the thing about material specifications, okay? What you are seeing here are minimum standards. The last thing that a steel mill wants to happen if you're on a construction project is to see these specs violated. The honest truth is that if you buy a piece of A36 steel off the shelf and go test it in the lab, it's going to have a yield stress of probably like 42, 43, 44, maybe even 50, and the tensile stress is going to be much higher. Okay. The idea is that what you see here, these are the minimum standards that the steel has to meet. Okay. it exceeds it, guaranteed. But from a design standpoint, you take the worst case scenario. What happened during the Northridge earthquake? After the Northridge earthquake happened, they did a lot of structural investigations, and they found that a lot of steel frames that were not supposed to fail, yeah, they did, okay? And one of the reasons why is because of this range. So the amount of ductility that we expected, we didn't quite get, okay? Because the material exceeded the minimum stress ranges, okay? So what the spec is doing is just letting you know that, yeah, you're going to use 58 for the purposes of design, but just be aware that you got a little bit of a range on the ductility side of things. That's why it's giving you that range. Does that make sense? Okay, now this grid over here on the side will tell you the applicable shape per grade of steel. So like for example, if you're purchasing a channel off the shelf, chances are that channel, that C-shape, is going to be A36 steel. You could get the channel in A572 grade 50 or something like that, but by and large, the preferred material specification is A36, okay? The preferred material spec for HP, that's what we use for piles, is A572 grade 50. W-shapes is A992, it's off the screen. So if you're purchasing something off the shelf and you don't know what the steel grade is, chances are it's probably the black square. If it's white, you can't find that product in that grade. So just something to keep in mind. Does that make sense? Okay, any questions so far? All right, so let's talk about hot rolled products. And what I mean by hot rolled products, and again, my heart's broken that the audio in that video didn't play. But essentially what we've got is we take molten steel, we cast it into billets, and then we use pressurized rollers to roll it into a given cross-section, akin to taking dough and rolling it with a rolling pin into a desired shape, okay? So hot rolled steel is generally produced in two main fashions, okay? So the first is to produce things like flat bar or round bar, to which, that's just plate. You can take that steel and make anything out of it, okay? So we can make like plate girders, connecting elements, threaded rods, things like that. That's kind of the first way. The second way is to actually take that steel and roll it into shapes, such as W shapes, channels, angles, etc. Okay? So those are the products that we're going to be using, okay? One of the things that you will very rarely hear me use the term of in this class, this is probably wild to think that in steel design, Dr. Mike isn't going to say this, you will probably very rarely hear me use the term I-beam, okay? Because we don't really use I-beams anymore. Standard rolled I shapes, S shapes, we have them, but they're not as common as wide flange shapes, hence the W shape. Wide flange shapes, their geometry is more optimized to handle compression and flexure and things like that. And so W shapes are the more common product that we use for most commercial steel construction, period. So W shapes are really what we're going to use. So you'll probably hear me refer to W shapes much more than I say the term I-beam, okay? Now, some terminology, okay? So just to make sure we're on the same page, so if you have an I-shaped cross-section, the top part and the bottom part of that I-shape is called a flange, okay? And the middle part is called the web, okay? Like Spider-Man, okay? If I'm talking about an angle, I am talking about the legs of that angle, okay? So that's what each of those components are called. So we might have angles where we have different size legs. So one's a long leg, one's a short leg. Okay. On rolled shapes like W shapes, the flanges are always the same size. Okay. Not necessarily the case with plate girders. Okay. In bridges, so how many of you got to go on that tour of the Nitro Bridge, the Nitro St. Albans Bridge? You were there. Did anybody else get to go see that bridge? You were there? Okay. So if you were there on that site, I guarantee you that the flanges of that girder was not the same size. In other words, it was a different size top flange than it was a bottom flange. That is very common in the land of bridge design, because what we find is that as we start placing load on the system, the compression flange and the tension flange see different effects. They also behave differently. Tension flanges like to yield and fracture. Compression flanges like to buckle. Different mechanics means different sizes, but plate girders are tailored to their load demand. For building design, we can just use one of the commonly available rolled products, so both of the flanges are the same size. Okay, so far so good? Now, terminology. A bit ago, I pulled up a W27 by 129. What exactly did that mean? Okay, so if I ever use the term W27 by 129, here's what that means. So there's a W, okay? The W corresponds to what type of shape I'm looking at. So am I looking at a W shape, an M shape, a channel, a C shape, WT, ST, etc. Every shape in the manual has a classification to it, bless you. So most common shapes that we're going to be looking at are W shapes. So W is the shape classification. The 27 refers to the nominal depth. And what I mean by that is if you group all of the W27s together, about average, they're about 27 inches deep. That doesn't mean that all W27s are exactly 27 inches deep. The one we just looked at a little bit ago had a depth of 27.6 inches, but it's around that depth, okay? So a W27 is about 27 inches deep. The 129 refers to how heavy it is. So a W27 by 129 is a W shape that is about 27 inches deep that weighs 129 pounds per foot. So if this was a W27 by 29, every foot would weigh 129 pounds, okay? So what we're going to find later on when we get into design is that our goal in design is to produce the lightest cross-section available. So if I tell you to pick the lightest W27, what you're going to do is look at this last number, and whichever section works that has the smallest number, that's the lightest section. Why would I care about designing or choosing the lightest section? Well, the lightest section means less steel. Less steel means less money, right? So we're going to find a section that works, but once that section works, we want to produce a design that's cost effective, okay? That makes sense? Now, if we're talking about angles, angles tend to be named something like this. So if I had an L6 by 4 by a half, the 6 and 4 are the lengths of the legs, and then the half is how thick the legs are in inches. Just throwing a little bit of terminology at you. Does that make sense? All right, any questions so far? This isn't hard, is it? This isn't all that difficult. All right, so that's actually all I had for today's lecture. Now, here's what's going to happen when we come back after break. We're going to come back and we're going to jump right into it, okay? The very first element that we are going to learn how to design in this class is a tension member. Now, I'll just tell you, tension members are among the most basic structural element there is. I mean, it's literally take a piece of steel, yank on it. Size it so that it doesn't fail. I'm telling you, that's it. But what you're going to find very quickly is that in the land of tension members, there are a lot of details that you need to account for when designing. I'll give you an example. How many of you have ever done any type of mechanic work or worked on your car, a lawnmower? How many ever gotten your hands dirty and used a socket wrench in your life? Okay. What happens if you take a 1/2 inch diameter bolt and try and stick it in a hole that is a 1/2 inch in diameter exactly? It won't go in, right? So you have to the hole has to actually be drilled a little larger to withstand the bolt, right? How much larger, right? That might sound silly, but those are details we have to account for when we're detailing steel connections, right? So there's a difference between the bolt diameter and the hole diameter, right? It might sound silly. Those are important dimensions, right? How many bolts do you consider effective when transferring stress? How do you handle bolted patterns that are staggered versus bolted patterns that are grid-like? What are the different limit states that you assess? How much of the area is effective in transferring stress? There's a lot of little detailed, nuanced questions. The reason why I like to start with tension members is because it gets you used to this. It gets you used to the manual, okay? You're gonna have to open it up, look at various sections, reference different charts, reference different aids and specifications. And so it is a good section, a good place to start because the concepts are really easy to follow, but the actual nuts and bolts of getting into the design of steel structures, that's what I want you to learn. That was a good pun and just went over. I was proud of that one. It just was dead. Broke my heart. I'm just kidding. Any questions? That's all I have, everybody. I'm going to pull the code up again in case everybody missed it, but we will see you all on Wednesday.